Welcome back to the Rock the JVM channel, folks. I'm Daniel, and in this video, I'm going to show you FS2, one of the popular libraries in the Scala ecosystem. So FS2 comes from Functional Streams for Scala, or FSS, or FS2 for short, and it's one of the popular libraries in the type-level ecosystem. And in this video, I'm going to show you some features in this amazing library. Now, this will assume that you're comfortable with Scala, and as a bonus, you have some basic cats effect concepts that I talk about in other videos here on the Rock the JVM channel or in great detail in the course. Obviously, as before, for maximum effectiveness, I recommend that you write code with me in this video, and whenever you need to refresh your memory about FS2, just refer back to this video or to the written form at the blog with the link in the description as always. Alright, so I'm going to move back to my dev environment, and unlike other videos, I have some minor code here that I've already written so that I don't have to type myself. And in this FS2, I'm going to continue the examples that I set for some other libraries here in the Scala ecosystem, including Doobie. And I'm going to continue the examples that we set there with a fictitious MyIMDb kind of use case application where we store movie information and actors. And in this case, we have a small data structure that I called actor with 3 fields and a bunch of actors in superhero movies. Now, if you want to write code with me in this video, which I recommend you do, of course, you can find this code over at the blog post. So it's one of the first code snippets that you can find there. Of course, the link is in the description, as well as the library definitions. And the library definition just contains code.fs2, fs2-core, and the version at the moment of this recording is 3.2.4, which is applicable for both Scala 2 and Scala 3. The code that I'm going to write in this video is 100% compatible with both Scala 2 and Scala 3. In the blog post, you will also find some Scala 3 native code. Alright, so what is this FS2 thing? FS2 is a library that describes streams. Now, what are streams? They're not necessarily data structures with a potentially infinite amount of data, but there are abstractions that will allow you to process an unbounded amount of data. So streams do not necessarily need to store the entire data, although many streams actually do in chunks, as I'm going to show you in this video. But streams are a very general abstraction that will allow you to manage an unbounded amount of data in the backend of your application. Now, this application has a main method because I've done that out of reflex, but I'm going to remove that, and instead, in my object, I'm going to extend IOApp from cats effect. So IOApp.simple, and I'm going to define my run method, which returns an IO unit. Now, you probably know from cats effect, if you're studying FS2, you probably know the cats effect ecosystem, and IO is an abstraction that will basically describe any kind of computation that might perform side effects. And this run thing will return an IO, so this will return an IO of type unit. And I'm going to import IO from cats effect, which is a dependency of FS2. Now, in order to see things to the console, I'm going to define an extension method, and because I'm writing Scala 2 in this video for better IDE support, I'm going to use an implicit class, but you can define an extension method if you're writing Scala 3. So I'm going to call this IO debug ops, or something like that. That takes a type argument A, and an IO as an IOA. And I'm going to decorate an IO with a method called debug that will return the same kind of IOA, and I'm going to say IO.map, and considering a value that this IO might store, I'm going to print line an S-interpolated string, and I'm going to add a small tag to say thread, current thread, get name, and then I'm going to print this actual value, and then I'm going to return that same A, so that this IO might be further composed along the way. All right, so this debug is just an extension method that will allow us to print the value that an effect can contain. Of course, if you're writing Scala 3, instead of writing this implicit class, you would write an extension that takes a type argument A, and again, a parameter which has an IOA. All right, so instead of implicit class this, you would write extension, and you would be all good, all right? Because I'm writing Scala 2, that doesn't compile, all right? Good. Now, what are some examples of streams? The first and the very simplest examples of streams are pure streams. So pure streams that store some actual data. And I'm going to define my Justice League actors. And as you notice, we have two sets of actors, one for the DC Comics and one for the Marvel Comics, and this is the Justice League and this is the Avengers. And for the Justice League actors, I'm going to say stream invoked with, and I'm going to use the stream from FS2. So I'm going to import fs2.stream. So that we don't confuse that with the Scala standard library stream, which is now called lazy list. We might have noticed a deprecation sign there. So notice that we are using the appropriate apply method for FS2 streams, and I'm going to push a bunch of actors there, and I'm going to copy pretty much every single actor here. I'm going to copy these and paste them here, and I'm going to put a comma there. And I'm going to import my data object, and of course I have all my actors here. Now, as I mentioned earlier, streams are an abstraction to manage an unbounded amount of data as your backend application continues to run. And this stream will manage, in this case, a finite amount of data denoted by these little variables. Now, this is a stream that contains two effect types. One is called pure, that I'm going to import from FS2, and the value type, which is actor in this case. Pure is an effect type, and in this case, pure is an effect type that does nothing, unlike IO, for instance, or option, or some other meaningful effect types. Pure is some effect type that does absolutely nothing. You can use other constructors. For instance, I can push or emit a single actor, so let's call this Tom Holland stream, as stream.emit. Emit is a method that takes a single value as an argument, for instance, Tom Holland, and this again returns a stream which contains an actor, and the effect type is called pure. That doesn't do anything or perform anything. If you want to push more values to a stream, not a single value, there is a plural method called emits. Let's call this Spider-Man, Spider-Men, plural, as stream.emits, and you can push any kind of sequence. And I'm going to use a list with Tom Holland, we have Andrew Garfield, and Tobey Maguire. Now, this abstraction works best with Cat's effect libraries, but if you want to turn the content of a stream into the Scala standard library data types, you could convert a stream to a standard library data structure. For instance, a list. So if I want to say Justice League actor list, I can use JLActors, the stream, .toList. This is only applicable for stream of type pure. Because if we have another effect type, for instance IO, those IOs need to be evaluated. So these streams, much like IOs, are lazily defined or lazily described data structures that will be evaluated upon a command, which for streams is called compilation. I'm going to show you a little bit later. Cool. So you can convert a pure stream to a list, to a vector, to whatever else you like. Now you can also process infinite streams. And from finite data, the only way I can turn this finite data into an infinite stream is to repeat that data. So I can say, let's call this infinite JLActors as JLActors.repeat. So this is what I mean when I said that a stream is an abstraction that will manage an unbounded amount of data. This infinite JLActors variable doesn't actually store all my actors ad infinitum, but it's the description of a stream that will produce these values ad infinitum when invoked. And I can force the evaluation of this infinite JLActors by converting that to a data structure. So I can say repeated JLActors list as infinite JLActors, and I can use a transformer like take. So take, for instance, take 10, and then I can convert that to a list because this repeat transformer will transform a stream of type pure actor into a stream of the same type. So the type will continue to be stream of pure and actors. And this take transformer will process the exact same types. Cool. If you want, you can test this out. So in the run method, I'm going to return IO with repeated JL actors list, and then I'm going to call debug on that to actually print the contained value, and then I'm going to use void to turn this back into an IO unit. So let me go ahead and run this little application, and we're going to see 10 actors in a list. So IO compute 4 is one of the threads managed by Cat's Effect, and the value is list with all these actors. So 0, 1, 2, 3, 4, 5, and then going back to 0. So 0, 1, 2, and 3. So we have 10 actors total. Good. So this is how you can convert actual values to a stream and then evaluate that stream as a data structure. You can also do effectful streams, which are far more useful in actual practice. And the easiest way that we can do an effectful stream is to evaluate an IO inside a stream. So let's say I want to save this actor Tom Holland into my database. I would do that under an effect IO, and I would define that, let's call this saving Tom Holland as a stream where the effect type is, in this case, IO, not pure, and the value type is actor. And I would use stream.eval. Stream.eval takes a single argument in the form of an IO actor, and I would have an IO with, let's say, print line, saving actor Tom Holland into the database, and then I would say thread sleep for 1 second, for instance, and I would then use Tom Holland as my actual value. Obviously, this is a fictitious example, but every IO can be passed as an argument to stream.eval, and this is an effectful stream in this case. So the stream will evaluate this IO only when pulled. This is the technical term for forcing the evaluation of a stream. Now in this case, saving Tom Holland cannot really be converted to a list because this IO needs to be forced. So I'm going to show you, for instance, saving Tom Holland.toList does not exist. So the toList method only is present for pure streams because there's no effect to evaluate, but rather I would have to compile a stream to turn that into some actual values. And let's call this compiled stream. I would say saving Tom Holland.compile, and then I would have drain. And this will be a simple effect IO of type unit because we're not really using the value contained in the IO. Cool. So if I want to print this out, I would say compiled stream because this is an IO unit, and let's see what we get if we run this application. Of course, instead of the drain method, which discards all the values inside the stream, you can run any other kind of method, including toList, fold, count, last, and so on and so forth, all of which convert the stream to an effect evaluating to a particular data structure, either list or option or whatever the method returns. Now, the next thing that I want to show you is chunks, because streams are built out of chunks of data. So you can build chunks out of standard collections or options, and then you can pass those along to a stream constructor. So for instance, if I want the Avengers actors, I'm going to copy all of them. So I'm going to copy all these actors, and I'm going to define a value. Let's call this Avengers actors as another stream of type pure and actor. I can use stream.chunk. And stream.chunk is a factory method that takes a chunk of particular effects, and I'm going to use chunk.array. And I need to import chunk from FS2. So chunk.array, and then I'm going to pass an array, so standard library array with all of these actors. Now I'm going to put a comma after all of them, all right, so that everything is in order. And this is an analogous to the Justice League actors that we built earlier with the stream apply factory method. But here in this case, we used a chunk constructor. So a chunk is a segment of data evaluated under an effect. In this case, pure, because we don't really need to do anything with these values. They are simply pure values. All right. So this is just another way of building a stream out of chunks. Now, you can also run transformations. For instance, because we have two streams of actors, one with Justice League and one with Avengers, and all of those streams are a stream of pure and actor, we can combine them. So I can say all superheroes, heroes, assuming I can spell properly, I can say JL actors plus Avengers actors. So ++ is a concatenation of streams such that this new stream will produce all the values described by JL actors and then all the values produced by Avengers actors. Now, a very popular transformation is flatmap. And flatmap has a very similar semantics to regular data structures such as lists. And in the meantime, you can also change the effect type of a stream. I'm going to show you an example. So let's call this printed Justice League actors. And in this case, I'm going to obtain a stream of IO and unit. So notice that both the types of the streams have changed. Instead of pure, I have IO, and instead of actor, I have unit. And I'm going to use jailactors.flatmap. And considering every actor inside the stream, I will perform an IO of type unit effect. So here, I will perform an IO unit effect. So I'm going to use stream.eval. And I'm going to use io.println with that particular actor. Now notice that this IO unit effect is performed as a stream because I'm using flatmap. So as is the case with, for example, lists, flatmap takes a function from an element to a list, and in this case we take a lambda from an actor to another stream. But in this case the stream type is different because the effect type was performed here under stream.eval, and unit here is the type of the effect being returned. Of course, this IO might have returned another data type which would have been reflected in the type signature of the resulting stream. Now, this flatmap plus eval thing is so popular that there is a method combining the two that's called eval map. So I'm going to say printed JL actors version 2 as jailactors.eval map, and I'm going to use io.println. Now you can also use flatmap plus eval, but also keep the same type as the original stream. So this is basically flatmap plus eval while keeping the original type, and that is called eval tap. So I'm going to use val printed jailactors version 3 as jailactors.eval tap with io.println. So for every actor contained in the jailactors, this effect will be performed, but the values will be kept. So this will be a stream of IO and actor in this case. Alright, so these are some of the essential features of FS2. In the next video, I'm going to expand upon that, and I'm going to describe some more advanced features, including pipes, resources, and concurrency with FS2. If you like this video, go ahead and click the like button for me and subscribe to the Rock the JVM channel for more videos like this. Check me out on Twitter and LinkedIn because I post fresh updates on upcoming material, and check out the Rock the JVM website and blog for hundreds of hours literally on Scala, functional programming, Akka, Cat's effect, and so much more. Until next time, I'm Daniel signing off.